Okay, so we are all the way up to chapter 3. The first chapter talked about what chemistry is. The second chapter was about the idea of the atom and how it's developed, and just different things dealing with just elements and atoms. This chapter is where the magic starts to happen. We're going to see how compounds form. We're going to learn that different elements will combine to make compounds. Not all elements will. And we're going to learn about what types of elements like to react with one another, and the type of compound, what type of properties it will have. So get ready. We're going to start by going back to the periodic table, looking at a couple different ways that we can represent elements, and then we'll start putting them together. So to help us figure out how elements are going to combine together, we're going to go back to the periodic table. So make sure you've got a periodic table sitting in front of you. I will have one on the screen here over the next few slides. Now there's different ways that we can represent how reactive a particular element is, and different ways that we can show that. One of the ways is by looking at what we call an electron configuration. The electron configuration states that, just like in Bohr's model and Schrodinger's model, that the electrons are filled for the atom in certain shells. So we can do it like a really simple Bohr's model where we have these shells of electrons, and each shell can only hold so many electrons. Well, when we compare that back to the periodic table, what we find is that the shells relate to the rows or the periods. There are 7 rows, there are 7 periods that you could look at. So the first row has hydrogen and helium. The second row, or the second period, starts with lithium and it goes all the way to neon. So 7 rows that we can look at, 7 periods. Each of those periods or rows is considered to be one shell. So we have 7 shells of electrons that we could deal with. Now, as we talk about electron configuration, generally we just do the first 3. Now the first 3 are limited in size. The first shell can only have 2 electrons. That's it. So if you have a great big atom, the first shell will only hold 2. The second and the third shell will hold 8 electrons each. So we go 2 and then 8 and then 8 more. Now, as we start building up these shells of electrons, the ones that actually react are always located in the outermost shell. That outermost shell is called the valence shell. So we're concerned about the valence electrons. Valence electrons. Now these valence electrons, so we're going to look from anywhere from 1 to 8 electrons in that outermost shell. They are related to the reactivity. So how much or how little does this particular element want to react? And it turns out, another kind of nice handy thing, is that those valence electrons, the number of them, is also the same as the group number. Now with this group number, this is going to be what we call the North American way of identifying those electrons. So I might have to find a quick periodic table so we can go over that really quick. So when we look at the number of valence electrons, it relates back to what group it's in. But over the years, there's been some disagreement over how to number the different groups. I know, crazy as it may seem. Not traditionally, today we number what's according to what's called IUPAC, International Union of Pure and Applied Chemistry. So they have a bunch of chemistry nerds that get together and they decide as a group how they're going to name or number, or what type of standards are they going to hold. So what the IUPAC decided whenever they discussed this, is they would just number the groups. Remember, those are the up and down, those groups. They were just going to number them from 1 to 18, and that's actually what you see listed here. So the little numbers on top, 1 through 18. For what we're talking about today, though, that's not necessarily the easiest way to look at it. So I'm going to show you an alternative to that. It's called the North American version of numbering the groups, and we're going to use A and B groups. I use this a lot in class. I don't mean to confuse you, but when I refer to it, this is what I'm going to be talking about. Now, what we've done is we've taken the periodic table and we've separated it into two areas, A's and B's. A's are called representative elements because they're just a little bit easier to work with. The B's are called transitional, and well, you'll hear more about those later on. Now, for the A's, and that's all we're going to look at today is the A's, we're going to start with the very first group is called 1A. Now, to number, they actually use Roman numerals. So we have 1A, and then we have 2A, and then everything down here in the middle, those are B groups. They also have numbers, but I don't use them very often, so we'll just say they're the B groups. Now, coming back over to one of these taller groups, this is 3A, 3A, and then we have group 14 is 4A. Do you remember how to write a 4 in Roman numerals? It's 1V, 4A, and then we have 5A, and 6, that's VI, and 7 is VII, and 8 is VIII. There we go. And what we'll find is whatever the group number is, that's the same as the number of valence electrons or electrons in the outermost shell. So if it's in the same group, if it has the same valence electrons, they have very, very similar chemical characteristics. Because do you remember the other name that they give for those groups, that nickname that they have? Let's check on the next slide. So another name that you could have for those groups, those vertical columns, is a family. So let's see here, let's write this up here. Family. So what I've done is I've actually put a picture of my kids on this slide. Not just to brag about them because they're all very sweet and all that good stuff, but just to show you this idea that if they're in the same group, there's often some sort of characteristic that's the same. So if you look at my kids, this particular picture was taken in Washington, D.C. a couple years ago. They're standing in front of the Washington Monument. You can see that 3 of my kids especially look very, very similar. Their hair color is almost identical. So my daughter is the oldest. She is standing second, and then my 2 younger boys, all blondish brown hair. My oldest boy, he has dark brown hair. All of my boys have blue eyes. My daughter has some hazel eyes. So there's these characteristics that you see. And if you put Kat with the younger 2 boys, I've actually had pictures where people were calling them triplets, even though there's an age gap in there. There's some sort of a characteristic or something about it where they all look very similar to one another. Does that mean they act exactly alike? No, not at all. But there are some characteristics that they all will share. And you'll often see that. One of my coworkers, Mr. Barker, used to always laugh at me and he'd say, oh, there's another Lumley kid, because there's just some characteristics about them that look very similar. Well, let's see how that works for our actual elements. All right, so make sure that you have your periodic table sitting out so you can refer to it for this part. What this one does is it again looks at what's called an electron configuration. Electron configuration. Configuration, that's a big old word. And so we're trying to figure out in what shell electrons like to go in. Now, to figure out the number of electrons that an atom has, remember the number of electrons and the number of protons, or the atomic number, is the same, assuming it's a neutral atom. So if you look at hydrogen, find hydrogen on the periodic table. It has a number 1, generally on top. That refers to that has 1 proton. Because it has 1 proton, it also has 1 electron. That first electron is always going to be in the first shell. Now that's the only electron that hydrogen has, so we can represent that electron configuration by writing the letter H. That's the chemical symbol or the chemical formula. Now, some books will draw circles. Other ones, you can actually just draw like a little half circle, and you can say it has 1 electron. Sometimes off to the side, they'll write the number of protons, like they'll write +1 or something like that. What you need to know is that hydrogen has 1 shell, and it has 1 electron in that shell. Now, helium has 2 electrons in the first shell. Well, it relates back to the periodic table. The shell, or the number of shells, is equal to what row it's on. So if you're in the first row, like hydrogen and helium, you only have 1 shell of electrons. If you're in the second row, so lithium over to neon, you're in the second row, you have 2 shells. And it continues down from there. Well, that's going to tell you how many shells, how many little half circles that you're going to draw. But when you figure out the number of electrons, that's the same as the group number. So number of valence electrons, VE is going to be valence electrons. That's going to be equal to the group number. And the group number that we use is going to be that North American version using the A's and the B's. So I'm just going to pick a few random ones in here to help you with. So let's look at lithium. We'll start with lithium. Lithium has 3 electrons because it has 3 protons. So I'm going to write a +3 to indicate that it had 3 protons. Now lithium is in the second row, the second period. So I'm going to draw 2 circles, 2 little half circles or quarter circles, whatever you want to call these. They're not really even circular, but you know what I'm talking about. In the first shell, you can have 2 electrons. So I'm going to put 2 electrons right there. Now, you could draw dots and big circles like the book did right here. I'm not too worried about that. I'm just looking at the number of shells and how many electrons are in each. So the first shell has 2 electrons. So I have 3 total. I've used up 2. I have 1 left over. That 1 is going to be in the second shell. It has 1 electron. Okay, keeping going. We're going to jump just a little bit. Let's go ahead. We can look at fluorine. Fluorine's right here. So fluorine, let's see here. Looking at the periodic table, it has 9 protons. So 9 protons. I have 9 electrons then to mess with. Now fluorine is in the second row, so we're going to give it 2 shells of electrons. The first shell of electrons can only have 2 electrons. That's it. Be 1 or 2, that's it. So any remaining ones that I have are in the second shell. Now the second shell can have up to 8. And we're going to see that with neon. Neon has 10 electrons total. The first shell of electrons is 2. The second shell is 8. When you add these together, it's going to equal your total number. The number of shells is the row number. The number of electrons in each shell is equal to the group number based on the North American numbering system. All right, so let's try one that's not actually listed on this particular slide. I know it's kind of cramped in here right now, but I think we'll be okay. We're going to try aluminum. So find your periodic table, find aluminum. You'll find out that aluminum has 13 protons, meaning that we have 13 electrons to play with. Now, aluminum, let's see here, it's in the 1, 2, third shell, so it gets 3 shells of electrons. The first shell of electrons can only hold 2 electrons. The second shell of electrons can hold 8. Well, it goes 2, 8, 8. So let's see here, I've used 10 so far. I have 13 total. That means I'm going to have 3 electrons in the outermost shell. Now, this particular way of identifying how many electrons there are in each shell It's useful, but it's not my favorite way. So I wanted to demonstrate it for you. I could easily ask a question about how many electrons can be in a certain shell, or if you're looking at a particular element, how many electrons are going to be in each for that particular one versus the maximum number it could hold. So be familiar with it, but I'm going to show you my preferred method here in a couple of slides. Now, before we go too much further, we need to go back to that periodic table because there's certain groups on that periodic table that have really common characteristics with one another, and it makes those particular elements very unique. In fact, they're so unique that they actually have special names. So let's look at a few of those just really quick. Now, in the upper right-hand corner, you see a picture of a little dropper dropping water on an element, and it's bursting into flames. Yes, there are certain elements that if you put them in water, they will burst into flames. That's kind of cool, isn't it? That happens to be sodium. Sodium's a metal. Sodium is a component of your table salt. Now, just because sodium likes to burst into flames, it does not mean salt will burst into flames. Salt is a compound, and elements, once they're put into a compound, will often have different characteristics. So let's look at some of these special groups, special names. The first one we want to look at are the alkali metals. Okay, in your mind, what does metals think of? It's going to be something that's a solid. It's probably going to be hard. It's going to have maybe a silver color. It's going to be lustrous, meaning it's very shiny. This particular group, the alkali refers to the fact that if you put them in water, they all form alkali solutions, or they have a high pH. They're basic. They're not acidic. These are also very reactive. Sodium is an example of an alkali metal. If you put it with water, it's going to burst into flames. Now, not all of them will do that, but there's actually a couple that will. This is group 1A or group 1, depending on, well, which version of the numbering system you want to use. Those are called your alkali metals. It includes lithium, sodium, potassium. They're very reactive. In fact, they're so reactive you'll never find them by themselves in nature. They're always in some sort of a compound. Group 2A, or just group 2, those are your alkaline earth metals. So these are also all metals. They're all solids, but they're not quite as reactive as group 1As. So these would include beryllium, magnesium, calcium, barium, different elements like that. And we're going to deal a lot with the alkali metals and alkaline earth metals. Now what we're going to do is we're going to go to the other side of the periodic table, and we're going to look at the halogens. Now halogens are in group 7A or group 17. Your halogens include fluorine, chlorine, bromine, iodine. These are nonmetals. They're very colorful. We have everything from a pale greenish yellow gas to a purple solid. They like to form compounds within themselves, making themselves what are called diatomic. And they also like to combine a lot with your alkali metals. And when they do, it actually forms what's called salt. And that's what halogen means in Greek, is salt forming. So those are your halogens, and we'll deal a lot with those halogens. Now, quick question here. If this halogen, say chlorine or bromine, is located in group 7A, how many valence electrons does it have? Oh, you're right, 7 valence electrons. The last special group that we want to talk about is the noble or the inert gases. This is group 8A, or group 18. They used to be called inert meaning that they don't react with anything, but then they found out, you know what, there is a little bit of limited reactivity, especially when you get to the larger ones. There's even some that's radioactive. So instead they call them the noble gases. So think of noble gases like the nobility, kings and queens, and they don't really want to interact with other people. They're fine by themselves. These don't like to react very much at all. This is neon, argon, helium. They just don't like to react. The two things listed at the bottom, well, this is going to be the middle and the very, very bottom part of the periodic table. The middle part of the periodic table, I referred to them as the B groups earlier, B groups. These are called the transitional metals. Now, again, they're all metals, but they don't quite act the same way every single time. They're a little bit harder to predict. So if they're if they're losing electrons, they don't like to gain electrons. If they're losing electrons one time, they might lose 1 electron. The next time they're going to lose 2 electrons. And so it's just, I don't know, it's just a little bit more difficult to work with. So we'll talk a little bit about how we're going to deal with these transitional metals. The inner transitional metals are located at the very, very, very bottom of the periodic table. Bottom of periodic table. Now, these actually belong in the middle of the periodic table. These are very large elements. They have some unique characteristics about them. A lot of them are actually radioactive. And for this particular class, other than the nuclear portion of the class, we don't deal a whole lot with intertransitionals. But I'll show you where they're at on the periodic table here in a couple slides. So here's just a very basic periodic table. Let's point out some of the important things that we've learned. Group 1 or Group 1A, well, these are your alkali metals. Alkali metal. Group 2A right here, these are your alkaline earth. Oh, I forgot my E. There we go, alkaline earth. Group 7A are called the halogens. And group 8A are called the noble or inert gases. One thing to point out, notice how noble is spelled. It is not spelled N-O-B-E-L. This is Nobel. This is a guy's name who has a very interesting story. The other thing that this particular periodic table points out, the color that's listed for the element symbol, notice most of them are black. The black means that it's a solid. The black means that it's a solid. On this periodic table, red is a liquid. However, most of the times it's blue. Most times they're listed as blue. Or in blue. And on this periodic table, if it's blue, again, most are red, it's a gas. Don't ask me why they did that. They just wanted to confuse you. So if you notice all of these over in here, all of these are all gases. The little red ones, those are going to be our liquids. Let's see here. What else does this one show? Oh, the yellow versus the green versus the blue. So there's this dividing line right here. This is the dividing line between our metals and our nonmetals. Usually there's another row right underneath that, and it goes straight down from there. Then your inner transitionals would be way down here. If it's on this side of the line, if it's on the left-hand side of the line, it's considered to be a, my pen is not wanting to write here. Oh, that's kind of frustrating. All right, if it's to the left of that line, it's a metal. If it's to the right of that line, so here's right, these are non-metals. Oh, yeah, now it likes to write. Non-metal. Over here is a metal. There we go. And if it's in a green, the green is also, oh, didn't want to write again. It's also what's called a metalloid. Let me see if I can write it up here. Also metalloid. So if it touches that line, right, left, top, bottom, that dividing line between metals and nonmetals, except aluminum, all of the rest of them are considered to also be metalloids. All right, let's keep going. All right, here's just another periodic table. A groups, alkaline metals, alkaline earth. The rest of the A groups, A. So this has your halogens, your noble gases. The other, what we call representative elements, they don't necessarily have special names. The transitionals are located in the center. Transitional. Sometimes I will metals. Sometimes I will also refer to them just as the B groups. And down here at the very, very bottom, my pen doesn't like to write down there. These, wow, it doesn't like to write. These are the inner transitionals. I wrote it on there. You can't see it. It liked to track my finger instead. There we go. Inner transitional, and I'm misspelling words today also. Inner transitionals. I forgot my N in the middle there. It's been a rough day. Inner transitionals are at the very bottom. Now these actually belong right here. What we should do is we should spread the entire periodic table out. Well, let's see what that would look like. If we were able to expand the periodic table out, this is where the inner transitionals go. Now, this wouldn't work very well on a normal, like 8.5 by 11 sheet of paper. So what we've done is we've pulled those to the very bottom, and then we pull the rest of the elements back together. Just know that they actually belong at the bottom, or in the center of the periodic table, excuse me, even though we usually list them at the bottom. This one is also showing that dividing line between metals and nonmetals again, just to make sure you know where those are at.